Good evening, everyone. Welcome to York's Observatory Teletube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We're broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. Teletube broadcast every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have about our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. And you can also connect with us on Twitter or Instagram with the handle at York Observatory and Facebook at Alan I. Carswell Obs. I am Matt, and I'll be one of your hosts this evening, along with Maheen, June, Dhyan, and Amin, as well as Professor Elena Hyde. Tonight, we've got a great presentation about gravitational waves. But first of all, the observatory at your campus is in Toronto. And to welcome you to our show, we would like to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area known as Sikaronto has been taken care by the Anishinaabe Nation, the Haudenosaunee Confederacy, and the Huron-Wendat and the Métis. It is now home to many indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts are but the latest in a very long history of astronomy in this area. And before we get started with our main show, we want to give you a little update on what you can see this coming week. There are a few things that will be visible tonight in the night sky, although there is one astronomical event in specific that was really interesting to behold if you had the opportunity to do so. Neptune's opposition was yesterday. And why is that an exciting thing? Well, if you're not familiar with what an opposition means, it's not actually a hard thing to understand. Basically, when a planet is in opposition, the solar system is aligning such that the planet lies on the same side of the sun as the Earth. And now, in order for this to happen, the planet needs to be on its perigee, in this case, as close to Earth as it can be. And we're talking about the planet that's furthest out in the solar system, Neptune. So having it at its closest approach to Earth and align with it, and the sun, well, it's a pretty big deal. That only happens once a year. On September 14, 2021, yesterday, at about 9 at the Universal UTC, sorry, you would have had the opportunity to see Neptune as close as it gets to us. So make sure to let us know in the chat right now if you had the chance to look at Neptune, maybe with a telescope or something. And I didn't have the chance, and if you're like me, I guess we'll have to wait for one more year to have the chance to do it. But till then, we can try to spot Vega and Arcturus in the night sky, as well as another really bright star that's also visible tonight from Toronto, Deneb. And make sure to check the planet Jupiter as well, because it's also going to be up there as bright as ever. And well, of course, well, it has to be bright, right? It's the largest planet in the solar system and my favorite one for sure. And speaking of things in the sky, there's another special event happening this week. So I'll let Professor Hyde give us some information about this special event that's going on right now.
Thanks very much, Matt. This is Professor Hyde just chiming in here for a little second to let everyone know that there is a very special event, in fact, happening tonight during our broadcast. As the broadcast goes through tonight, we are getting closer and closer to a very, shall I say, inspirational event. That is the launch of Inspiration4. This is the first all-civilian mission. That's right, no astronauts allowed. Hopefully launching this evening in, oh gosh, about 28 minutes or so. So we're going to have our regular show, but at some point when we get close enough to launch, if it doesn't get canceled, we will go ahead and cut over to the live broadcast so that we can watch the launch with you and talk about it a little bit. So this is a very, very exciting event that we're hoping to be able to enjoy with you live, and we will so expect a little bit of a cut in, if you will. over to the Inspiration launch. And before we get too distracted by space launches and all that stuff, we are going to start telling you about gravitational waves. So if you're not sure about gravitational waves, or maybe you've heard the name and you don't quite know what they are, we actually have June here to give us an awesome explanation to get started. So I'm going to go ahead and say, go ahead, June.
Thank you, Elena. Now, you may have heard of gravitational waves or gravitational radiation before here on the Alan I. Carswell Observatory's Teletube or elsewhere in recent years, and may be wondering, what are gravitational waves? First, it helps to define radiation and talk about some similar forms in our everyday life. Radiation is essentially just energy propagation. Electromagnetic radiation, or light, as it's also known, is electromagnetic energy in the form of small wave packets called photons. This is probably why we say that something that emits light is radiant. More intuitively, sound waves are also known as acoustic radiation. Sound is a pressure wave consisting of propagating vibration throughout matter, and the energy it carries is kinetic energy. Gravitational waves are similar to sound waves, but instead of expanding and contracting air as a wave, gravitational waves expand and contract space-time. This change in space-time is incredibly small because gravity is a weak force compared to other forces like electromagnetism. The oscillations in space-time we observe here on Earth due to extreme events in the universe are smaller than the size of a proton and are completely negligible to us as we go about our everyday lives. Still, scientists are curious little creatures and spent decades developing theories, models, and even hardware and experiments to detect gravitational waves. Talk about making a big deal about something so small, am I right? Gravitational waves are pretty far removed from everyday life, so let's make a metaphor to explain why these small waves are making big ripples throughout the scientific community. Imagine space-time like a body of water, and picture two massive celestial bodies as two boats. One boat can push on the water to make a wave, but the water will push back and the boat will move. This is a simplification of why paddling while you swim causes you to move throughout water. You may know that Einstein's general relativity describes gravity as the curvature of spacetime, and says that matter pushes on spacetime, telling it how to curve into form, and then spacetime tells the matter how to move throughout it. The boat making waves is much like a massive moving celestial body bending spacetime, and our second boat will be impacted by those waves and thus feel the boat's presence. The two boats can interact with each other purely through these waves, altering their trajectories throughout the water, similar to two celestial bodies who are gravitationally bound. Let's imagine that a distant observer on a boat wants to study and observe these other celestial boats. Well, they would get out a telescope and point it at the boats and see the light coming off the boats towards the observer. Astronomers have been doing this type of science since back in Galileo's day, and it's given us a fantastic understanding of the ocean of a universe and the boats within it. But let's make these boats practically invisible, as in they don't emit light themselves. Like black holes in our ocean of a universe. Well, that makes studying them with a telescope very, very difficult and requires indirect observations by observing visible boats being affected by invisible boats and making inferences about said phantom boats. Wow. Those astronomers are pretty clever, like little creatures coming up with a method for that, like that. But hey, you ask, why are we observing the effects of waves on one boat, on another boat, to tell us about the first boat? Why don't we just cut out the middleman and observe the waves directly? When observing with light on visible objects, this is simple, because the light waves from the objects can be seen by our eyes. But invisible objects like black holes require us to spy on them with other types of waves. Gravitational waves. Now that we can detect gravitational waves, we can see this space-time ocean much clearer and study not only those elusive dark objects, but study the ocean of space-time itself and how these waves propagate and behave. That's really exciting. Those scientists have really outdone themselves, don't you think, Amin?
Thank you for the excellent introduction, June. The detection of objects and phenomena in space usually requires the use of electromagnetic radiation, such as visible light, X-rays, radio waves, microwaves, and more. Other types of particles may also potentially be used in the future, such as neutrinos. Each of these different types of viewing gives different types of information, and they complement each other. Gravitational waves are a bit different, though. They have nothing to do with the emission and detection of particles, but are instead based on ripples in spacetime itself. These ripples can provide completely new information about the universe, information that was not accessible before. For example, colliding massive black holes can be detected. The detection can be done by indirect methods or by direct observation using ground-based detectors. Indirect observations use studies of objects and interactions in space, while direct observations involve the usage of interferometers. Events that produce gravitational waves are extremely violent. Unfortunately, by the time gravitational waves reach the Earth, the waves become billions of times smaller. Before interferometers were created, there were some indirect ways to measure these waves. The main example that was used was the Hulse-Taylor binary system. This system consists of a neutron star and a pulsar orbiting each other. We can detect a lot of information about this orbit using the Doppler effect and other methods. Using that information, the amount of gravitational waves released can be predicted. As the two objects spiral toward each other, energy is lost and emitted as gravitational waves. The closer the spiraling gets, the more intense the waves become. Calculations can be made from observations, but the observations of the Hulse-Taylor system and others like it are not direct. For direct observation, an interferometer is needed. The term interferometer comes from the words interfere and meter. These devices take two beams of light, which are lasers, and merge them to create an interference pattern. An interference pattern results from overlaps of the peaks and troughs of waves. In the interferometer, light is sent across the device as reflected to later recombine in two arms. If the light beams travel the same distance in the interferometer, the result will be total destructive interference, and there will be no light detected. Gravitational waves cause space to stretch and contract. This could make one arm of the interferometer longer and one shorter. If that happens, the distance traveled by the lasers will change, and there will no longer be a perfect overlap of the light waves. This will be seen as a signal of light detected at the end. The gravitational wave effect is actually very hard to detect in this way, though. The change in the length of the arm could be much smaller than even an atom. Interference from effects on Earth like shaking can also interfere with the result. LIGO stands for Laser Interferometer Gravitational Wave Observatory, and it's the largest interferometer on Earth with 4-kilometer-long arms. And actually, it consists of two interferometers, which are located 3,000 kilometers from each other in the United States. A successful detection needs more than one interferometer to detect the same signal in different locations, which would verify that the gravitational waves are passing over a large area and that the signal is not just a fluke. In LIGO, the detectors are L-shaped. Mirrors are used to deflect the light and create the interference pattern, and the photodetector receives the light. Due to the size of the interferometer and other limitations such as the power required for the laser, many ingenious corrections were implemented for the detector to work. On February 11 of 2016, LIGO announced the first ever detection of gravitational waves, the first ever direct detection. The source was two massive black holes merging at a distance of 1.3 billion light years away. Another detector also verified this measurement, and it's called a Virgo. Virgo is also a large interferometer, and it's located in Italy, but it involves cooperation from many other European nations. It has also detected the same gravitational waves that LIGO found, and its inclusion to this field of study has increased the accuracy of finding the source of the waves by around 10 times. Virgo can detect gravitational waves that are frequencies of 10 Hz to 100,000 Hz, Hz being cycles per second. This is quite a wide range. The arms of the interferometer are 3 kilometers long. Unfortunately, Virgo is currently not running and is under suspension due to the COVID-19 pandemic. During this period, however, both Virgo and LIGO are being upgraded to improve the sensitivity of the detections. Some interferometers are being planned for usage in space. These include LISA and DESIGO. LISA stands for Laser Interferometer Space Antenna, and it is a proposed group of spacecraft which could orbit the Sun. Instead of having physical arms, the interferometer will be created by 3 satellites with a separation of millions of kilometers. This would allow for a much higher Munsell sensitivity compared to detectors on the ground. DESIGO stands for Decihertz Interferometer Gravitational Waves Observatory, and it is another proposed mission from Japan. It would work best in the range of 0.1 to 10 Hz, frequencies which LIGO and LISA are not good at. The design of DESIGO is similar to that of LISA, containing 3 satellites in a triangle shape. This time, the separation length will only be around 1,000 kilometers. We'll have another speaker who will discuss the future of gravitational wave observations. But for now, up next is Dhyan, and he'll discuss the interpretation and uses of gravitational waves.
Thank you, Amin, for the excellent information. And now let's talk about the uses for gravitational waves and how they can be interpreted. So as Amin mentioned, historically, scientists have relied almost solely on electromagnetic radiation to study the universe. Things such as visible light, X-rays, radio waves, microwaves, etc. And this has been possible by the use of telescopes. And to be honest, it has gotten us pretty far. We have a significant understanding of the universe. But to understand how electromagnetic radiation works, we need to understand the electromagnetic spectrum and how telescopes use them. So, as mentioned, there are multiple types of electromagnetic waves. And what telescopes do is that they detect a specific portion of the electromagnetic spectrum that is given off from objects such as stars, galaxies, and black holes. And then using lenses and mirrors, they create enlarged images of these objects. Scientists often use multiple images taken through multiple telescopes to study the universe. And as you can see, has been very useful in studying the universe. But using one method can only get us so far. So in order to understand the universe better, we need to find a different method. And this is where gravitational waves come into play. Gravitational waves and electromagnetic radiation provide different but compatible views of what our universe looks like. Electromagnetic waves interact with matter very strongly. For example, light bends around a mass, it can be distorted, reflected, absorbed, and etc. This complicates how we are able to view the universe. But gravitational waves, unlike electromagnetic radiation, interact very weakly with matter. They travel through the universe basically uninterrupted, which can give us a simpler and a clearer picture of the universe. Gravitational waves have many uses, as I will discuss next. So first off, the discovery of gravitational waves has no direct effect on us and our lives, but this discovery has brought us one step closer to the theory of everything. The theory of everything is a hypothetical framework that proposes that there is a theory out there that can explain all known phenomena in the universe. And researchers have been searching for this theory ever since the development of quantum mechanics and general relativity in the 20th century. A theory that can explain all laws of physics is the ultimate dream. And this discovery has brought us ever closer to it. Because not only does it prove Einstein's general relativity, but it also predicts the existence of another particle known as the graviton, using a concept in quantum mechanics known as wave-particle duality. Wave-particle duality is the concept in quantum mechanics that states that all matter can be described as a wave and as a particle. And this came to fruition with the double slit experiment. Electrons were shot through two slits and they were expected to make a pattern that can be seen on the left. But instead, what occurred was an interference pattern, the image on the right. And what's so mind-blowing about this is that the interference pattern was analogous with that of waves, proving that all matter behaves as a particle and as a wave. And all of this could greatly help humanity advance to the next level technologically. Things like efficient space travel, cryogenics could become a real possibility. It's truly an exciting time in science. And now, moving on to another good thing about using gravitational waves to study the universe over electromagnetic radiation is that some things in the universe don't interact with electromagnetic waves, things like dark matter. And in those cases, gravitational waves can be used. Dark matter is a substance that does not interact with electromagnetic force, meaning it does not emit, absorb, or reflect any light. Now, this makes it extremely hard to detect. But why is it even important to us in the first place? Well, studies show that galaxies in our universe seem to be rotating at speeds that shouldn't be possible. The gravity generated by their observable matter isn't enough for these galaxies to be held together. This has led scientists to believe that there is something else that interacts with gravity in order to hold them together. And this something is known as dark matter. Now, it is believed that visible matter only makes up about 5% of the universe, and dark matter makes up about 27%. So we know that there is a lot of dark matter out there in the universe. But since it's so hard to detect because of its interaction with gravity, it's extremely difficult to detect since it only interacts with visible matter through gravity. Scientists think that dark matter can be detected through gravitational waves through several methods, though, and here's how. Firstly, scientists think that dark matter might be primordial black holes. What are primordial black holes? Well, imagine right at the beginning of the Big Bang when matter starts to form, and as the universe expands, the growth of matter starts to occur everywhere. And in some places, growth of matter might be more dense than others. And this could have caused the matter to collapse under its own gravity, forming early black holes. Now, unlike normal black holes, these primordial black holes don't have a minimum mass threshold, meaning they could be smaller than our sun. And if LIGO were to detect these gravitational waves from such black holes, it could prove the existence of dark matter and give us an understanding of the beginning of our universe. Secondly, we know that dark matter only interacts with visible matter through gravity. But based on the behavior of known particles and the fact that these particles interact with each other, scientists think that dark matter particles could also interact with each other. And if that occurs, dark matter could form compact dark objects. These dark objects would then interact with ordinary objects such as stars. Now, if dark matter does exist in such large quantities, making up almost 30% of the universe, then there should be a lot of compact dark objects. And some of these dark objects might interact with supernova candidates like stars. These stars and dark objects could coexist peacefully without much disturbance through gravity. But when the star does go supernova, it would create a huge disturbance between the resulting neutron star and dark object, sending ripples of gravitational waves throughout the universe. If LIGO was able to detect these waves and track them back to their original destination, it could prove the existence of dark matter. And lastly, another dark matter candidate known as an axion. Axions were first theorized in the 1970s when scientists noticed that neutrons do carry charge within them, but the charge is so symmetrically and uniformly spread that it cancels out, making the neutron an electrically neutral particle. And they credited this theoretical particle axion for it. This particle could exist in a vast amount, and it would hardly interact with matter. Currently, scientists think that axions form clouds around black holes, and when two axions annihilate each other, the gravitational waves could be detected by a high-frequency gravitational wave detector. And on that note, I will pass it on to Maheen to discuss the current and future research with gravitational waves.
Actually, we're going to do a little bit of a live update here for our broadcast. This is Dr. Hyde. I'm back again. We have some breaking astronomy news. We don't normally do this, but in a very exciting times that we live in, there's all kinds of amazing launches happening. And one of those is actually happening mid our broadcast. So I'm just going to hop on over to the live screen here for what is known as Inspiration4. So you'll all have to forgive this a little bit of segue. We're moving away from dark matter to things we can see. A very exciting astronomy space mission happening right now. This is Inspiration4. This mission is due to launch in about 10 minutes. So because this is a live broadcast, of course, we're live here with you, and we could not resist the chance to watch along for this launch. The Inspiration4 is the first ever all-civilian mission launched by the planet Earth ever into space. So we had all kinds of interesting space launches over this last year. We had, of course, Virgin Galactic and Blue Origin compete with suborbital flights, which were actually run by the very wealthy individuals who set those companies up, and they spent only a few minutes in weightlessness. But this launch is something altogether different. Inspiration4, which is launching in 9 minutes, that's 9 minutes, and it hasn't been delayed. You can see the rocket there on the side. The live view is the 4 astronauts who've been selected actually first ever civilian astronauts. These are 4 civilians going to orbit Earth on a SpaceX Crew Dragon spacecraft. This is very, very exciting times. So breaking astronomy news. We'll come back to your regular programming here shortly. And we have, of course, all kinds of things happening. These 4 individual, civilian astronauts are all very, very unique individuals. And they were bought a ticket by, again, a very wealthy person, a billionaire. It's actually unknown how much the Mr. Isaacman, who chartered the flight with SpaceX, had to spend. But the 3 civilians they took with him are actually people who have won contests, won raffles, and the mission itself is actually a fundraiser. That's right, a space mission as a fundraiser for a children's research hospital, St. Jude's. This is absolutely unprecedented, and we only have 7 minutes to go. So very exciting times. We're going to be with you here live for the next 7 minutes, fingers and toes crossed for this rocket launch. Now, I know all of our crew tonight has secretly snuck aside a few little fun facts about Inspiration4. Does anyone want to go first tonight and share what their thoughts are on this first of a kind launch?
I can go first.
Go for it.
Well, the spacecraft being flown tonight is the Crew Dragon Resilience, which was actually last flown on the Crew 1 mission last November by NASA astronauts under the Commercial Crew Program to the International Space Station.
Absolutely, and this is a great example of now individuals being able to pay to go into space on chartered flights with SpaceX. And as June mentioned, this is the Dragon spacecraft, the same one that NASA used to send astronauts to the ISS. So NASA is buying flights, and so did this fellow Isaacman. And he's, of course, chosen to take with him three individuals who are also civilians. This is the first flight, however, with no astronauts on it. I believe all 4 civilians had to do about 6 months of training and get relatively fit, but they did not have to fulfill astronaut criterion, which you and I all have trouble with. Dhyan, would you like to go next and introduce the astronauts?
Yeah, so there's 4 astronauts going today, and so the first one, obviously, Jared Isaacman, who's financing this entire mission. And then there's Haley Arkenaugh, who is a nurse, and she's a cancer survivor. So she's a very, very brave, strong person. And then there's Chris Sembrowski. He's a U.S. Air Force veteran. And then lastly, there's a geology professor who was a finalist to actually become a NASA astronaut. And his name is Cian Proctor.
Oh, that's her, Dr. Cian Proctor.
Oh, sorry.
Yes, she's an amazing person. But yes, she's a professor, she's a pilot, she's an artist, she's an educator. She was a previous NASA finalist, and she won a very large competition, actually, to use the payment system that the billionaire came up with. So amazing person, and still a civilian. So, any more fun facts on our astronauts?
Yeah, I can do it.
Amin, go ahead.
Yeah, so the CEO of the company funding the mission, Jared Isaacman, who we mentioned, he actually started his company in his parents' house's basement in 1999 when he was 16 years old. And he's actually going to be the commander of the flight. It's not surprising because he actually is a jet pilot. He's flown civilian and military planes, and he actually holds, I think, a couple of world records. He said he's fulfilling a personal and lifelong dream. I recognize the tremendous responsibility that comes with implementing this mission, etc. So it's pretty inspiring.
Absolutely. It is super inspiring. And they've only got 4 minutes to go now. So everyone's probably just biting their fingers, and they look so relaxed in that capsule. But I can tell you they are almost certainly not relaxed. They are civilians. They've all had extensive training. Of course, Jared Isaacman, he has pilot's experience, as does Dr. Cian Proctor. And they have people actually functioning in multiple roles. So you have Haley Arsenault, who was a physician assistant at St. Jude's Hospital, as well as being, of course, a cancer survivor, who has medical training. And they're actually going to be doing medical tests on themselves once they get up, and they'll have 3 whole days in space. I think it's 3 entire days, but very close to 3 days, if not more, where they will be weightless. They will be in low Earth orbit. And this is really exciting. Low Earth orbit, that's around 575 kilometers, or for those of you in the miles system, 357 miles or so, but straight up. Now, 575 kilometers, that's about sort of the distance from Toronto to Montreal. If you're in Canada, it might not seem incredibly large, but going straight up is really, really hard. And at that orbit, they will be around the same area as a lot of satellites. They'll be around the same area as the International Space Station, and they will be fully weightless in space. So it's really, really exciting. And there is actually, if you want even more on this, they are in the process of producing a Netflix show to go along with this. And there's a whole bunch of episodes about how they did their training and interviews with all of the different astronauts. And it's worth noting that Dr. Cian Proctor, she is actually coming up as only the 4th Black female astronaut ever, which is absolutely amazing. So they're on their final 2 minutes. Maheen and June, you both want to go real quick here?
Sure, yeah. So just adding on to what you mentioned earlier, definitely a notable thing about the mission is that it is a part of an effort to raise $200 million for St. Jude Children's Research Hospital. Reason being that Isaacman wanted it to really mean something, and thus he led a campaign to raise money and awareness for childhood cancer research, which definitely makes this mission really stand out from many others, other than the fact that this time civilians are going into space. So yeah.
Exactly. And if you go to their streaming site, you will actually see a running total on the donations. I'm seeing currently over 200,000 US on the donation page as we speak. So I'm not sure what the grand total all in will be, but it looks like they're on their way to having that 200 million raised. It's never been done before, to my knowledge. It's very, very exciting. So we're on the last 30 seconds here. I think we should probably do a little bit of a countdown, and then June, you can talk about the cupola. You can see they're starting to make hand movements. We're on the last 20 seconds. You can see there's some steam looking stuff coming off of the rocket. It's getting ready to go. And this is, of course, the SpaceX rocket Falcon 9. So this is one of the famous reusable rockets where the boosters will come down separately. And here we go. Fingers and toes crossed, everyone. And the camera is shaking. That's some flames. Oh boy. Oh, you're so exciting. But I would fingers and toes crossed for them on their way up out of the gravitational well of Earth. And wow, there they go. This is it's called Inspiration4, and it is truly inspirational. So we're all hoping them all the best, and it is, as Maheen has said, very scary, exciting. So this is live, right? So nobody knows how it's going to go. Rocket launches are always unpredictable, but this is now plus 46 seconds. They're on their way, lifting off, and you can see at the bottom, they've got a little chart here showing how far they need to go. So once they go for startup, they're going ahead and they're posting the speed as well as the altitude, and we're going back and forth from camera angle. So this looks like it's the camera off the side of the rocket or the spaceship itself, looking down. I don't see Earth yet, but we're a minute in. Maximum dynamic pressure. This is the largest amount of stress exerted on the vehicle. So not for the faint of heart or the faint of nerves, because you really, really, really want it to go well. And this spacecraft is largely automated. That is why they're able to go. They're not actually doing a lot of the spacecraft operations themselves. It's meant to run almost without them. It's a fully automated flight, which just seems a little bit terrifying. But on the other hand, I don't think I'd want to try to drive it. So it's absolutely, absolutely crazy. But here they go, and yay! I don't know. It does. If I can get my co-host to turn off your microphones for a second, can we do a round of applause for them? We have everyone.
Hi.
Hello! Yay! Okay, so we'll do 1, 2, 3. Will that work? Let's
All
try.
right.
1, 2, 3. I don't know if it's coming across the videos, but there you go. Yay! Hooray! So space is scary. It's scary, exciting. Bite your fingernails. It's incredibly dangerous. We can't breathe in space. We can't do anything in space. We just be popsicles. Humans are not designed to live in space, so we have to bring a lot of protective things with us. We have to have a pressurized spacecraft. That spacecraft has to contain everything we need to survive. It has to have air, it has to have water, it has to have places to sit, it has to have food, because there's nothing up there. It's space is a vacuum, and as you've been learning about with our regular broadcast, of course, the gravitational waves traveling through space, being very, very, very subtle. Well, that's because space is just empty. It's a place where there are very few particles per cubic meter or centimeter. It's not got a lot of stuff in it. They are going to low Earth orbit, which is more occupied than some would like. It's getting quite filled up with satellites at the moment, but it's still incredibly empty, and they're still, it's funny to think, on the one hand, they're only as far away as Montreal is from Toronto, but on the other hand, it's straight up, and that makes all the difference when you're going into space. So I hope you all are as excited for them as I am. It is a absolutely groundbreaking event. So you can see the little subset here. This is the live action for the astronauts coming through. And we aren't pulling through their audio because it's actually on their channel. So if you'd like to go and watch them, it's Inspiration4 live stream launch. But we had to show it because this is breaking astronomy news. The first all civilian launch from the planet Earth. And it's on the SpaceX Crew Dragon capsule. And as I said before, we don't know exactly how much had to be paid by Isaacman to SpaceX to charter this flight. But the fact that it is now charterable, this means that we can have regular people going up. There's an engineer on here. There's a young woman with all kinds of metal bits in her leg. There's somebody who's had pilot experience. But a lot of these folks wouldn't have necessarily passed astronaut training. And as someone myself who would not have passed astronaut health requirements, this makes me very excited, because now I'm thinking, well, all right, so when's the next competition? Because I could go on this. If any of us had won the raffle, we could be up there right now, biting our fingernails in under actually a good deal of pressure still, because the rocket is still going. So you can see they're up to 164 kilometers altitude, again, going straight up, and they're going all the way up to low Earth orbit. So I think it's expected to be around 500 or so kilometers once they're fully in. All right, everyone. So this has been your live astronomy update. June, do you want to tell them a little bit about the cupola now that they're on their way?
Yeah. So the reusability aspect of this spacecraft is what's really making the cost come down. But they did make some modifications since this spacecraft last flew. So they removed the docking adapter that allows them to dock to the International Space Station on the top of the capsule, and instead replaced it with a really, really durable glass cupola dome that allows them to see up and down, depending on where the spacecraft is oriented, as they go around the Earth. So they'll be able to see the Earth through this big window. And if the spacecraft is pointing away from the Earth, they'll be able to see, well, space from there as well. And that really helps when you're traveling at 575 kilometers above the Earth. And I do want to add that this altitude hasn't been reached by a crewed flight since the Apollo and Gemini space programs.
All right, everyone. It's every once in a while you get a little bit of cross feeds. We think we've solved the audio issue now. Hopefully, we can get June back in at some point. And as mentioned, this dome cupola, if you will, it is an unusually large, extra durable sort of glass dome, and that will have been on a lot of the diagrams that you might have seen. It's almost a full hemisphere, so it's got a sort of a fishbowl effect. But this means you can go out and really get a very, very, very good look around. And one great thing about watching this live is, as we've been talking, you can see the altitude and the speed changing. And the overall stage 2 telemetry changing as well. So you've got your stage 2 and your stage 1. It looks like stage 1 is actually coming down. This must be part of that reusable rocket that we were talking about before. Now I'm going to go ahead and say this has been a wonderful segue. And if you have a chance, please do make sure to continue watching. As you can see, here they are on their path up to low Earth orbit. It will take them a little while to get there, but now you have seen that the launch is a success, and the astronauts are moving around in their chairs, waiting for permission to get out and float around, basically. As soon as it's safe, NASA will tell them, and they can begin to go out and about. So that is their downlink. So I'm going to pass this back to Matt. Can you grab the screen share? Wonderful job. All right. So a little bit of a segue away from dark matter, but very, very exciting. The astronauts are going to continue on their way for a little bit now. But if you do get a chance to tune in about, another 10, 20 minutes, so just after this broadcast, please go on back and see if they've managed to unstrap for weightlessness. Alrighty, so we're going to go and take a step back away from spacecraft. Now, as you're mentioning dark matter and detections, one thing you can do with awesome space launches is you can bring up space telescopes. And there's a fun space telescope design called LISA, which was actually been in the works for quite a while, where we would take telescopes up into low or even higher Earth orbit and use very, very, very large baseline arrays to basically replicate what something called LIGO has done down on the ground here on Earth to even detect gravitational waves. So if you wanted to get an even better telescope, you could try to convince SpaceX to take up your design into Earth orbit. But here on Earth, we don't do such a bad job. So let's go ahead and go back to Maheen. And just as an FYI, I believe you're on slide 18. And we'll pick up with the gravitational waves, and I believe we're going to get to LIGO as well.
Thank you, Professor Hyde. Moving on. Albert Einstein published his General Theory of Relativity in 1915, which gave the scientific community a treasure that consisted of theoretical predictions about nature, space, time, matter, and gravity. At the time, however, general relativity was not easily testable from direct observation and experiments. All of this changed in September 2015 when the Twin Laser Interferometer Gravitational Wave Observatory LIGO detectors registered gravitational waves from the merger of two black holes, as discussed by Amin in detail earlier. In just 3 short years, LIGO has contributed to a landslide of new discoveries. LIGO followed the initial 2015 detection with several more observations of black hole mergers. In August 2017, there came a major turning point when the first detection of a direct observation of a merger between two neutron stars occurred. Neutron stars are the dense collapsed cores that remain after larger stars die. The merger was the first cosmological event which was observed not only in gravitational waves, but also the entire spectrum of light, from gamma rays to radio waves. Many theories on dark matter have relied on the difference in reaction of gravitational waves and also light to the gravity of massive objects. However, the merger helped confirm that this is not the case, and their speed of travel is indistinguishable. On April 1st, 2019, after receiving a series of upgrades to its lasers, mirrors, and other components, LIGO's twin detector now have a combined 40% increase in sensitivity, but suggests that it can survey an even larger volume of space than before. Virgo, which is the European-based gravitational detector, has also almost doubled its sensitivity, and thus both LIGO and Virgo are set to resume searching for ripples in space and time and help in the advancement of research on gravitational waves. Currently, scientists from the Center of Computational Relativity and Gravitation are involved with several observatories in order to identify gravitational waves from objects similar in mass to our Sun, with the help of LIGO and Virgo, from supermassive black holes in the center of the galaxies with the help of Pulsar Timing Array, PTA, and Laser Interferometer Space Antenna, LISA, and from known pairs of stars in our galaxy with the help of LISA. Each of these experiments help examine gravitational waves from a distinct frequency range, and thus measure some of gravitational wave radiation from different astrophysical sources. Pairs of black holes, which are a million times more massive than the Sun, may be circling one another, generating ripples in space itself. NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, has spent more than a decade to find evidence of these ripples created by behemoth black holes. In January 2021, a signal was detected, which may be attributable to gravitational waves, though it is not definitive. In order to confirm this observation, more research will have to be done. However, if proven, this will be a milestone in gravitational wave research. The team at LIGO and Virgo are constantly trying to improve the sensitivity of their instruments, allowing them to see increased volumes of universe, and thus opening doors for more research on gravitational waves. One of the large-scale interferometers, Kagura, located in Hyde, Japan, became operational only a few years ago and has begun real-time observations in its quest to detect gravitational waves. LIGO India project, which is a planned joint India-US detector, will be the construction of the third LIGO interferometer and is a big step towards building a large global network of gravitational wave detectors. Worldwide network of widely spread facilities is needed for the extraction of the best information from the gravitational waves. Another project that has a great potential for gravitational wave research expansion is Laser Interferometer Space Antenna, or LISA. It is led by the European Space Agency and plans to launch 3 satellites which will each settle into an orbit 1 million kilometers apart from the other 2. Earth-based interferometers consist of arms which are long vacuum chambers. but space conveniently provides its own vacuum. These satellites can be linked together via laser beams and will act together as a single interferometer. I know this sounds like something out of a sci-fi movie, but it's actually very close to becoming reality. The LISA satellites are planned to be launched around the mid-2030s. Quote, the real payoff of gravitational wave research is going to be in the future, unquote, said Rainer Weiss, known for his contributions in gravitational physics during the post-Nobel press conference. Well, everyone, you have been listening to the Alumni Carswell Observatory's weekly Teletube broadcast, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Matt, June, Amin, Dhyan, and myself, Maheen. Make sure to leave any comments or questions in the comment section of the video or talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, see our website at observatory.info.yourq.ca. You can always connect with us on Twitter with the handle @YorkObservatory and check out our website for show notes, content updates, and contact info at observatory.info.yourq.ca. Thanks for tuning in. Clear skies and have a good night.
And just as a follow-up, if anybody is still watching around, we'll do a extra special thanks to Inspiration4, which has successfully launched today. It is now 18 minutes after successful launch, and they are now doing all kinds of fun checks over on the Inspiration4 launch stream. So if you're just coming off the end of this broadcast, I highly recommend to go on over and check it out. They are doing final checks and office work, but they should hopefully be allowed to do some waitlist bobbing about pretty soon here. So thanks again, everyone. Have a great evening.